Hello everyone. In this video, we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular, we will continue to unpack the photoelectric effect. Alright, so in the last video, I described in some detail the 4 surprising results from our photoelectric effect experiment. And we want to know, fundamentally, how these 4 results can be explained. And the answer is, as you might have guessed, the photon model of light. This is from Einstein in 1905, who initially characterized this sort of using Planck's initial idea. But he really sort of expanded on it, described what was going on, and gave a model for what is happening. And he said that to explain the photoelectric effect, we can appeal to a model of light in which what light is light is composed of quanta, discrete bundles of energy, where quanta or quantum, a quantum, is a packet. You can think of it as a packet. Discrete means not continuous. So a little chunk, a particle in this particular case. And he characterized their energy as being directly related to the frequency. And this requires a little bit of explanation. If a photon model is a model in which light is a particle, you might ask yourself, frequency of what? All right. Now, we do already have an answer for that. We have the frequency of the various wavelengths of light. But if light is not a wave, then what do you mean by frequency? So that's our first question. The second is, okay, if the energy is related to the frequency, what is it related by? Well, it's related by Planck's constant. And this is an equation we've seen before, but this is the origin of that equation. Notice that Planck's constant is named after basically Max Planck's idea that the energy was quantized for light. It did come in these individual packets. And Planck's constant allows you to convert for light the relationship between the frequency of the light and the energy. And I want to stress this, for a wave, for any other wave, this is just a bizarre claim, okay? The idea that the frequency of the wave you send and the frequency alone is what determines the energy of that wave makes no sense from a classical theory of waves. High energy waves, like water waves and waves in a slinky, are all waves with large amplitude. The energy of the wave is proportional to the amplitude squared. It's not proportional to how often those peaks come at you. It's not related to the frequency of the wave itself. And here we're saying that for light, it's only related to the frequency. And we want to know frequency of what? And so the image to have in your head of what Einstein considered to be the photon is not quite a particle exactly, right? If this is our pure wave model, here's our wavelength of this wave, shown right here. What he had in mind is closer to what is known as a wave packet, which you might remember from when we introduced them in topic 9, or topic 4. A wave packet is a tiny little packet of waveness, all right? It's a couple of squiggles that move together. And those squiggles that move together do have a defined wavelength. So you can sort of draw lines from peak to peak in that wave packet and get a wavelength. So it has a well-defined wavelength and frequency. There's some uncertainty in it, which we'll discuss later. But it has a reasonably well-defined wavelength and frequency. Not only that, but if you sort of mentally draw a bubble around the whole thing, that whole thing is traveling, okay? It's going to be localized. Right now, our photon is right here, and the energy is in this particular packet. So this is a photon, and this is a model that sort of interestingly combines what we think of as a particle versus a wave. So this is a wave packet, and that is the model that Einstein was proposing when he proposed the photon model of light. So that radiant energy is quantized, only coming in discrete packets. That is, this isn't a good relationship or a good representation of the light coming from our source. These individual waves are not a good representation of that light. Instead, the thing coming from the source are sort of these individual discretized photons. So individual photons are traveling from the source to the photosurface in this experiment. And this is the model of light to have in your head, is a whole bunch of different wave packets. If you increase the intensity, you're increasing the number of these wave packets, the number of photons, not the energy of each photon. And the frequency is just related to the amount of energy sort of per photon, okay? This will allow us to explain all of the results. So all of the 4 results discussed in the previous video can be explained with reference to this photon model. One quick note before we move on. Notice that at this point, the intensity of this light is characterized as the power per unit area, and that power can be unpacked as the total energy being delivered per unit time. Notice that in this model, that total energy is distributed among the separate photons that are being sent. And in particular, we can unpack E total as n, the number of photons, times E gamma, the energy of each photon, equal to hf by the equation from above. And therefore, the intensity is equal to the number of photons times the energy of each photon, related to the frequency, per unit area, per unit time. This sort of conceptualization of the energy from the beam being chunked into these different packets is the essence of the quantum revolution, and the essence of what we will discuss as being quantum mechanics. And this started with the photon.